So we're going to go ahead and begin today with our Cornell notes. Today's subject is going to be 1, and let's go ahead and set up our paper here. We want to make sure that we have this done correctly. So if you recall, I know it's been a while, but this is the side of your paper where that red margin is. I believe the color is red, and you just lay a ruler down to mark that line. At the very bottom of your paper, I only need you to have about 5 lines where you're going to write your summary at the very end of your notes. And again, today's title is Waves 1. I'm going to give you about 30 seconds or so to go ahead and set that up. So we want to go ahead and write down the first 2 facts we need to have here. We kind of have an idea what waves are. I mean, you guys are familiar with ocean waves and, seeing, like, I guess, air blow flags around and things like that. And those are definitely waves. But we want to be more scientific with understanding what's exactly going on. So the first question today is, what do waves transmit? And the second question is, what is matter? And we're going to go ahead and answer those. Waves transmit energy through matter or space by disturbing the matter. Now, if it's just traveling through space, it's not going to disturb matter, but we'll get to that later. And the second part of this is understanding what matter is, right? Because if we're saying we're transmitting energy through matter, we need to have an understanding of matter. And matter is anything that has mass and volume. Remember that these are solids, liquids, and gases. And you have a choice. You can write down what I've written down with my green here, or you can just write down what's in red. I'm going to give you a chance to go ahead and get caught up with that. Now, we're going to go down to the next section. So just below where you wrote, you're going to add these 2 more questions and 2 more of these answers. And we're asking, what causes waves? That answer is waves are caused by vibrations. And the second, what do waves carry? We're kind of repeating ourselves here, but we want to remind ourselves that all waves carry energy. I'm going to give you guys a chance to write that, and then I'm going to take some time to kind of talk about it. So as we look up here at this drum, suppose I were to take this drum and strike it with these sticks. When I do that, that's going to cause this surface of the drum to kind of shake a little bit. And that little shaking motion is called a vibration. As this vibrates, it is going to cause the air particles around to also carry that vibration. And then when it goes into someone's ear, they're going to be able to hear that sound. And the idea here is that this energy, this is called sound energy or sonic energy. I'll say sonic energy also. This energy is traveling through the air to someone's ear so they can hear the sound. Now, this part right here, that's called the wave, right? So here's the energy coming from the drum. It's carried over the wave. And again, this is showing that the wave is caused by a vibration. Now, all waves, no matter what kind of wave they are caused by some kind of vibration. And all waves, no matter what type, now there's many types of waves, but no matter what type, all waves are going to carry energy. And again, if you want to add my drawings, you're certainly free to do so, but that is not required of you. Now, understanding what energy is, if we kind of talk about energy and what waves are carrying, we need to understand what energy is. And energy, what is energy used for? Energy is used to do work. In physics, we say work equals force times distance. But that is one way we have of defining energy. Remember that energy can change objects. Energy can also change environments. And I'm going to pause while you take a moment to write down what you wish to write down. Again, you can add my little drawings and writing if you wish, but it is not required. So here's an example. It says right here, waves in a pond make water move up and down, and things bob on the surface. So let's say you have, I'll put like a little pond here. There we go. We got some water. Okay. And let's say there's like a little toy boat on top of the pond. And as you're kind of like, letting your boat float out onto the pond here, you're noticing the boat is going up and down, and you notice the waves are moving across. Well, what's happening is this is a type of matter. And we are going to call that a medium. So the word medium just means a type of matter. So here, what is a medium? A medium is the matter that a wave uses to travel. Now, I would like for you to write down this example. You may draw my picture if you wish. You do not have to. But it says waves in a pond make water move up and down. Things bob on the surface. So again, if we are creating movement, then we are affecting objects in some way. And what this is showing us is that this is in fact energy that is moving across this pond. Just going to give you a second to get caught up here. Here's an image of that same pond water that I was discussing. And here you can kind of see this area. There's a wave, there's a wave, and there's a wave. You can see there's a space between these like high points. So I see three, let's say, well, here's a wave, here's one right here too. I see one there as well. So we can see like little areas where the water is higher and where the water is lower. But again, this is just exactly like what we were talking about. As this water is moving back and forth, it is carrying energy. We're going to go right here to wave motion. Wave motion, mechanical and electromagnetic. And I did add a couple of details here. As we're looking at wave motion, sometimes waves, so when all waves are moving, all waves move, but they can be mechanical or electromagnetic. The mechanical waves, I want you to remember that the word mechanical starts with an M, and I want you to remember that the word medium also starts with an M. And so that's easy for you to remember that all mechanical waves require medium. But if you look at the word electromagnetic, that starts with an E. So it does not start with an M. So there's nothing about electromagnetic that requires a medium. It does not need one. Only mechanical waves do. Another way of saying electromagnetic, though, is to simply say light. I'll give you guys a chance to get caught up before we move forward. Now, we can see two shapes of waves here. And I do apologize. I know that the print is very small here. There's a lot going on. But we have two shapes of waves. We have what's called longitudinal and we have transverse. Now, longitudinal waves are going to move parallel to the direction. So these are moving parallel. Whereas transverse waves are going to move, basically the energy moves up and down, but the wave moves side to side. So these move what we say perpendicular to the movement. We have a couple of pieces here. The distance from the center to the top, we call that amplitude. You can't really see it too well in this diagram, but that's going to be the distance from the rest position to the top or to the bottom. Again, that word is amplitude. And as you can see right here, it's just that area from that midpoint to the top, and it's the same right here. On a transverse wave, we also have what's called a crest, and that's this high part right here. And then the low part is known as a trough. You're going to see that here and here. Again, this is labeled. I'm just writing it for you because it's kind of hard to see. Now, on the longitudinal wave, we have these little tight areas where there's a lot of these little lines, and that area is called a compression. It's kind of where all the little wave pieces are pressed together. And this one, where it's kind of stretched out, that part on this diagram is called expansion, but in school we like to say that this is called a rarefaction. As you can see right here, rarefaction. And so those are the major parts of the wave. There's one last thing you guys need to know. If you ever want to know like just how long a wave is, you want to look at what we call wavelength. Now right here, you can go, and it doesn't matter what you choose, but you just want to choose two identical pieces of the wave. So here I'm choosing the trough from there to there. That is a wavelength. And then up at the very top, you can go from the center of one rarefaction to the center of the other one. That would be a wavelength. But you don't have to. Like, I could also just simply choose, like they did right here with this illustration, the center of the compression to the center of the compression. I could also choose the center of the crest to the center of the other crest. That would also be a wavelength. And we also have a special symbol for wavelength. I'm going to go ahead and draw that for you right now. To show a wavelength, we want to use the lambda symbol. And it's basically like an upside down Y. And it looks just like that. And this little symbol means wavelength. And I'll just tell you, in physics we have a lot of strange symbols we like to use, but that's one we really enjoy using a lot. All right, looking at mechanical waves, all mechanical waves are going to need a medium or some kind of matter to travel through. Okay, they need a medium or matter to transmit energy. And they can be of the two different types. They can be transverse or longitudinal. I'm going to give you guys a chance to write that before I move forward. And just feel free to pause the video if you need to. Now, electromagnetic waves, these are a little bit different. And I've kind of written some different types over here. We have radio waves, microwaves, infrared waves, visible light, UV, X-ray, gamma. And this is an electric disturbance and a magnetic disturbance at one time. So you have two different parts of this electromagnetic wave. I'll show you in just a minute what I'm talking about here. But they travel through space, not requiring a medium. So this is how the sun's energy reaches the Earth. It can travel without having to use any kind of matter, because there is no matter between the sun and the Earth. There's not air. It's called a vacuum. There's nothing between us. And that's how the light and heat reaches our planet. I'm going to give you a moment to get caught up, and I'm going to move forward. You can draw my picture if you want to. You don't have to. So this is an electromagnetic wave. This is so cool. I love waves. So you can see here there's like actually two waves in one. So this red part is the electric wave, and the blue part kind of going side to side in this transverse like format, that is the magnetic wave. So we have an electric field and a magnetic field that are moving at the same time. That's why electromagnetic waves are so cool. It's like really two transverse waves joined together. I am not going to ask you to draw that. It looks a little complicated to draw. I mean, if you wanted to, you could, if you're good at that sort of thing. But I just want you to know that when we say electromagnetic, we're kind of it's like a compound word, right? So if you look at it, electromagnetic. You have the electro part, magnetic part, and it's really because there are two waves in one. These are all the electromagnetic waves. And you might not realize this, but you can actually see electromagnetic waves. But here's the bad news. You can only see this tiny little part right here, and that's called visible light. So the color red is a different wavelength and frequency than the color yellow. The only difference between, like, let's say blue and red is that they have different frequencies. and different wavelengths. So if you look, here you can kind of see, the radio waves, those are really big. As I move into microwaves, they get smaller. Infrared, another name for infrared is going to be heat. So heat waves, those are infrared. And then you get into red, yellow, red, orange, yellow, green, blue, indigo, and violet. As you're looking at these, you can see these electromagnetic waves. But when we get to ultraviolet, that means above violet, you can't see those. They're very dangerous to your skin too. And then X-rays are a little bit more dangerous. Gamma rays are the most dangerous. And so one thing I want to tell you about is that as you get into higher frequencies, you're going to get into higher amounts of energy. One thing you need to understand about wavelength and frequency. So frequency is a number of waves in a second. Let's go ahead and define that for you. So frequency is the number of waves per second. High frequency is high energy. But one thing I want you to see here is that if I talk about wavelength and frequency, it has a negative correlation. If the wavelength goes up, the frequency goes down. And if the frequency goes up, so if we increase the frequency, wavelength goes down. If we increase wavelength, frequency goes down. So it doesn't matter which one of these you raise or lower, it's going to have the opposite effect on the other. They have what we call an inverse relationship or a negative correlation. So here we're talking about frequency again. Frequency is measured in a unit known as hertz, and we abbreviate that with Hz. So frequency is a number of waves that pass a given point in 1 second of time. We also want to define amplitude. So if this is my wave, amplitude is the distance from the center to the top or center to the bottom. Now, the amplitude can relate to how much energy a wave has. So I wrote higher amplitude equals more energy. And then lastly, we have the wave speed formula. So wave speed is velocity equals lambda f. And I just told you that lambda symbol represents a wavelength. I'm just going to give you guys a chance to get caught up with that. I want to give you guys a little problem here because I just love math. I'm going to throw some math in here. Why not? Math is fun. So let's say a wave has a wavelength of 2 meters and a frequency of 5 hertz. What is its, no apostrophe, what is its speed, right? So if I'm asking you this question, just set it up like the formula here, right? So just, let's just do V equals lambda F, and let's go ahead and replace our variables. So we know that our wavelength here, that's what that symbol means, that lambda symbol means wavelength. We were told that it was 2 meters. And we're going to multiply by the frequency, which we were told is 5 hertz. So, and by the way, remember that you always measure velocity in meters per second. And so in this problem here, my velocity would be 2 times 5, which is 10. There you go. There's your answer right there. Not too hard. I do want you to draw and label this image, this diagram of transverse waves. You do need to know all of this. So I'm going to pause the video while you do that. Make sure your drawing is neat. Make sure you have labeled the components there. And we're going to need to draw the longitudinal wave. There is no such thing as a longitudinal electromagnetic wave. Longitudinal waves can only be mechanical. I want you to go ahead and draw and label this diagram to the best of your ability. Go ahead and pause the video until you are done. And now we're getting down to our summary. Now, we have a problem. I have removed the words that you need to have here in the summary. You need to figure out what those words should be. Then I want you to go ahead and add 3 more sentences of your choice to the summary. Before, I would kind of give you the summary and you would just copy it. But now that we're getting closer to the end of the school year, we want to make sure that you guys are being more independent. And so I'm going to only give you this much help today. And I want you to work on this to see if you can figure out what that summary should be. Again, this is of your own making. When you are finished, your finished note should be looking something like this. You have these important questions on this side. You have some facts on this side. Now, when you want to study, you should fold this piece of, this side over a little bit so you can't really see what's written. And just go down this list and just ask yourself all of these questions. See if you can answer them correctly, and just open the paper to check your answers. You can kind of see the last part of the notes. You might have to use the back of your paper too. That's fine. But make sure that your notes are as legible as possible. Make sure that you can read them, because really these notes are a tool for success. Basically, you're going to be using these notes to study for your quiz so you can get the highest grade possible. And that can only happen if you have good notes that are clean and easy to read. And we are wishing you all the best for your quiz score. Remember that you can add to these notes over the course of the week, and that you can always modify these to make these personally valuable to yourself.